Good afternoon, friends. Today we shall be taking up graph theory, that is very much useful in networks problems. Now let us first of all define some of the basic terminologies, and then we will see how to use these terminologies and how to use the basic network laws in a very compact form, especially when you have multi-node, say hundreds of nodes in a network. Then solution of the network problems with different conditions, say voltages at different nodes may be given, some may not be given, and there are different types of elements, 4-terminal, there is 2-port network elements. So it is a complex mixture of different kinds of elements, passive and active. So solution of such networks become very involved. We resort to graph theory in such cases. Topology, it is a branch of mathematics. It is a branch of mathematics concerned with selected properties of collections of related physical and abstract elements. All right. In network topology, we include the particular configuration of nodes and branches. The configuration of nodes and branches without regard to what elements exist in those branches. Suppose you are having an inductor, a resistor, a capacitor. For example, when we apply Kirchhoff's law, currents flowing in these elements will sum up to 0, irrespective of the type of elements that you have in the network, is it not? So this can be used, this network topology can be used for different types of networks like water and gas mains, mechanical network, traffic flow, etc. See, network theory, this Kirchhoff's current law we can also apply to traffic flow, is it not? Number of vehicles moving towards a particular junction and number of vehicles going out at an instant, that will be summing up to 0. A graph is a set of lines we call lines or line segments known as edges. These are called edges. So each element in a network will be represented by a line or an element. Okay, these are called edges. Then intersection of edges will be known as nodes or vertices. Intersection of edges. Edges are incident only with vertices, they cannot hang, they will be always coming to a vertex. Okay. The degree of a vertex is the number of elements falling onto that vertex. Okay. A graph may be connected or unconnected. That means between any two vertices, if there is a path existing, all right, you may have between this point and this point, I can always find some path. Okay. So this is connected, this is a connected graph. Now consider a situation you are having a transformer winding, okay, n is to 1. Here I can put all these elements, generator as well as the resistance here, as a single edge, or if you want, generator can be shown separately. So, I can have another edge for this. Each element will be represented by an edge. Similarly, a capacitor by this, okay. Then there will be some leakage reactance here, resistance here in the winding, so that will be represented by another edge. This side, there is some leakage inductance here, mutual inductance, and on this side there is a resistance. So, these two are connected like this. So, this is unconnected. There are two graphs unconnected. You may have a circuit like this. There is a source, there may be a capacitor here, there may be a capacitor here, okay. So, I can number the elements E1, E2, E3, E4, E5, E6, E7 like that, and then I can number the nodes also. One, 2, 3, 4, 5, I may put one node here, 6, okay. Then 1 to 2 I will represent by an edge here, 2 to 3, like this, 3 to 4. E3 and E4, they may be combined, or I can put another node here after this element. So, that may be 1, 2, 3, 4, 5, 6, 7. So, 3 to 7, 7 to 4, 4 to 5, 5 to 6, 6 to 1, and 2 to 4. Okay. We can also write the element numbers against each of these edges. This is E1, this is E2, this is E3, this is E5, this is E4, this is E6, this is E7, and this one, if you want, E8 to be between 1 and 6. So, this will be the network graph for this circuit. Okay. So, this is the electrical network and this will be its graph. So, these are the nodes and these are the edges. Okay. A degree of the node 4 will be how much? 1, 2, 3. Okay. Now, we define some more terms. Tree, co-tree, loops, branches, rather twigs, and links. Suppose you have a network graph like this. Okay. We choose a particular orientation of the elements. We can choose the direction of currents arbitrarily in any network. We can select some current directions. Okay. So, we put those directions on these edges. Okay. Then this is known as an oriented graph. This is an oriented graph. Once we give an orientation to the edges, it is an oriented graph. So, we can give some arbitrary orientation to these elements, all right. Let these be 1, 2, 3 and 4. These nodes be 1, 2, 3, 4 and these are the orientations. We can number the elements also, the edges E1, E2, E3, E4, E5, E6, E7. Okay. Now, a tree is a subgraph which contains all the nodes, but there is no loop present. This can be a possible tree, all right. There can be a tree like this. This is another possible tree. This is another possible tree including E4, E6, E5. Okay. You can number the nodes every time. Elements also you can show. So, there can be so many possible trees. Okay. You put any other element, there will be a loop. Suppose we now choose E2, then there is a loop, is it not? So, a tree means there is no loop, but all the nodes are connected. All the nodes are connected. From any node you can go to any other node, there will be a path available. So, this is known as a tree. Okay. How many elements are there in a tree? Suppose the number of nodes is equal to capital N, say n minus 1. To connect n number of points you need n minus 1 number of elements, all right. So, we will call it twigs, okay, or many books write branches of a tree. More specifically it should be termed as twigs, because in many other books they term all the elements as branch of a network. So, there is a confusion. So, it is better to mention branch of a tree, or better to say twigs. Twigs means branches of a tree. So, number of branches for a tree will be n minus 1. So, number of branches in a tree will be n minus 1. If from the network, if I take out the tree, what is left is a co-tree. So, co-tree is the subgraph left after the removal of a tree. Of a tree from the main graph. Okay. will the core tree have interconnect all the nodes connected? May not be, not necessarily. So core tree can be an unconnected set of subgraph, whereas a tree is a connected subgraph where there is no loop but all the nodes are connected. So the elements of a core tree are known as links. Okay. So core tree is basically complementary to tree to a tree, okay, or the vice versa. Now suppose we have a tree like this in the previous example, then what will be the core tree? Core tree will consist of these dotted lines. Okay. If I choose this as the tree, then the core tree will be consisting of these dotted lines. If I choose this as the tree, then core tree will be these dotted lines, and so on. The tree can be this one also, then core tree is like this. Okay. Is this clear? Fundamental loop by fundamental loop we mean once you select a tree, you put one link at a time, and the loops formed by replacement of such links will be known as fundamental loop. Okay. So this is, if I have selected this as the tree, then this is a fundamental loop, this is one fundamental loop, this is one fundamental loop, and this is one fundamental loop. Okay. The loops are consisting of that particular single element and the other necessary edges of a tree, okay, to form that loop. That means the particular link is closing a loop, and that is a fundamental loop. This will not be a fundamental loop. That means a fundamental loop will consist of only one link. You may not, this may be a loop, but this is not a fundamental loop because there are two links. You take one link at a time, whatever loop is formed, that is a fundamental loop. Okay. Why do you need fundamental loops? When you are having a very large network, you keep on taking, while writing loop equations, you keep on writing loop equations. You never know what will be the order, how many loops are minimum required to solve the network problem. How do you really select the number of equations, number of loops, when especially you are having so many variables? So you select a tree, whatever is left over will be the links, that is elements of the core tree. Take one link at a time, that will be forming the loops. Okay. So number of equations, loop equations, minimum number of loop equations required to solve the problem will be number of links. Okay. So total number of edges is say E. Then what will be the number of links? E minus B. the total number of links will be total number of edges here 1, 2, 3, 4, 5, 6, 7, and how many are required to form the tree? 3. So there will be 4 fundamental loops because there are 4 links. Okay. E minus B will be number of fundamental loops. The minimal number of edges which, if cut, separates the graph into 2 unconnected subgraphs will be known as cut sets. Cut set means it is a set along a line of cut. So once again I have taken for the same network graph one particular tree like this, okay, and these are the elements of the core tree, that is the links. Now you cut one branch of the tree at a time and separate the graph into 2 subgraphs. So I can cut along this is a cut set, okay, fundamental cut set. Then I can cut along this is another fundamental cut set. I can cut along this is a third fundamental cut set, that is I am cutting this edge of the tree, I am cutting this edge of the tree, I am cutting this edge of the tree, okay. So you segregate the 2 parts by cutting one branch of the tree at a time, okay. There can be many other cuts possible. I can have a cut like this, I can cut 2 branches, that is also a cut set, but that will not be a fundamental cut set, okay. We choose another tree, then this particular cut may be a fundamental cut set. It all depends on the tree you choose, okay. Like in the previous case, the fundamental loops will be dependent on the type of tree that you have selected, and hence the type of links that you have selected, the elements that you have chosen as the link. Is that clear? So in a cut set, suppose these are the 3 directions of the tree elements, okay. When I have a cut set here, this is one cut, so the links here, 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 you will find these 3 links are getting cut along with this, okay, this particular twig. We shall be associating a positive direction to the cut set, particular cut set, according to the direction of the tree element. So this particular tree element is having this direction, so this direction will be taken as positive for the cut set, okay. Therefore if the direction of this element initially was chosen like this was the direction chosen, then this will be negative and this will be positive. If this element was having a direction like this, then this will also be positive, because the line of cut is taken as positive when the elements are going inside. I have selected the direction of the tree element as the reference, okay. So all other elements going inward for this cut set will be positive, all other elements will be negative, they will be given a sign negative. We will come to cut set matrix later on, alright. Similarly, if I have a cut here, then this is the direction which is taken as positive, so this element will also have a positive value. This element, depending on the direction, if this is the direction, then this will also be positive. So this is the direction of the elements and hence their signs for different cut sets. This is how it is selected. Now we define a matrix, incidence matrix. Complete incidence matrix A. We select say a direction for all the elements. Suppose this is 1, 2, 3, 4. This is element 1, 2. Suppose this is the direction. Okay. I put a circle on the node numbers and these are the edge numbers 1, 2, 3, 4, 5, this may be 6, this may be 7, these are the edge numbers. We give a sign +1 when it is going away from the elements in the A matrix. We will put +1 when it is going from node 1 to 2. If it is going away from 1 to 2, then against the node 1 we will put +1 sign, and against node 2 we will put -1 sign where it is entering. So, going away means +1, entering a node is -1, going away from a node it will be given +1, going into a node it will be given a -1 sign, and it is not present anywhere else, so it will be 0. So, for this we write the matrix like this. Elements or edges, there are 7 elements 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Okay. And nodes 1, 2, 3, 4. So, the first element is going from 4 towards 1. So, at node 1 it is -1 and at node 4 it is +1. Okay. Element number 2 similarly at 4 it is +1, at node 2 it is -1. So, this element will be -1 here, +1 here. Is that okay? Rest are all 0, so I am not writing them. Element number 3, could you please tell me?
+1 at 4.
And at node 3 -1. Then element number 4, element number 4 is +1 at 1 and -1 at 2. Okay. Element number 5 is +1 at 2, -1 at 3. Is that okay? And element number 6 is +1 at 1 and at 3 it is -1. Very good. And element number 7, it is +1 at 3 and -1 at 4. Is that okay? Now you see, if you add the columns, they are all zeros. Is it not? -1 -1, sorry. So, they will be summing up to 0. This. So, the equations that you write here, if I write 4 equations involving these element connections, one of them is redundant, because if you have 3 equations, 4th equation can be generated from the first 3 equations. First 3 equations can give rise to the 4th equation. When you have addition of these elements equal to 0, okay, then this is not an independent equation. Without that I can fill it up. Wherever there is -1, the rest are all 0, so it has to be +1, because total sum has to be 0. So this is -1, 0, 0, then this will be 0, then this will be +1. So any one of them, you say remove row 2. If I give you 1, 3, 4, you can always generate row 2. Is it not? Total sum has to be 0. So -1 and +1 is already 0, so there won't be anything, it will be 0. Here it is only 1, 0, 0, so this will be -1. So I can always generate row 2 even if it is not given. So information of row 2 is contained in 1, 3 and 4. Hence we define another matrix A, where any of the nodes is taken out as a reference. I can choose number 4 as the reference or number 1 as the reference, any one of them. So if I remove that, then this matrix will become, it will be 1, 2, 3, 4, 5, 6, 7, but on this side you will have 1, 2, only 3 nodes. That means number of nodes will be equal to 1 less than the given number of nodes in the network, original graph. Okay. So you can fill it up. So delete any of the rows of A matrix, you will get the matrix A. All right. So this is the commonly used incidence matrix, we call it A matrix. Now we will be going into some of the properties of these matrices. We similarly define loop matrix B. You choose a tree. Suppose this is a tree. Okay. These are the elements 1, 2, 3, 4, 5, 6, 7. You take one element at a time. So let us take this. Let me see the direction that we chose. This was the direction. This was element number 4, 2, 5. These are the directions 3, 7, 6. Okay. the direction of the loop is decided by the direction of the link. So the first loop loop 1, I will call it loop 1, is with this element 1, okay, link 1. Now that completes this loop, is it not? So you go along this loop taking this to be positive, alright. You take the reference of the direction of the loop as the direction provided by the link, okay. Link direction is taken as the direction of the loop. So if it is in the opposite direction, I will put a -1 sign. If it is in the same direction, I will put a +1 sign. So here it is 1, element number 1 it will be 1, element number 4 it will be 1, element number 2 it is -1, rest are all 0, no other element will be connected with this. Is that okay? Then loop 2, I can choose the second link as this one, then this will be the direction because the direction of element 3 is this. So element number 3 will be +1, element number 5 is -1, element number 2 is also in the opposite direction. So 5 and 2 will be -1, rest are all 0, okay. Then loop 3, I can choose this as the loop 3, third loop, where direction of 6 is +1, 4 and 5 both are negative. Okay. Loop 4, I can choose element number 7. So element number 7 is +1. What are the other elements? 3 is a link. 2 links will not form a loop. 2, 5, in a loop only one link will be present. So 2 and 5 will be -1, -1, okay. What was loop 2? +1, +1. What was loop 2? 2, 5, 3, -1, -1 and +1, okay. So these will be the elements in the loop matrix, B matrix. Is that okay? Matrix A, I can rewrite matrix A. Once you have selected a tree, you can put the tree elements in one side and the link elements on the other side, okay. We can put it as AT partitioned A link, okay. So what will be AT like? I will put the column numbers as element 2, 4, 5. This is my tree. So 2, 4, 5. I will partition it. Then 1, 3, 6, 7. 1, 3, 6, 7. I may fill up these two submatrices with ones, +1, -1 and zeros from here, okay. I know element number 1 is between 1, 4 is eliminated, so I know the elements here. So element number 1 will be having those elements here, okay. So I will get one AT matrix and AL matrix, two partition submatrices for matrix A. Similarly, we can also partition B. If we take B transpose, it will be like 1, 2, 3, 4, 5, and this will be loop 1, loop 2, loop 3, loop 4, and so on. Okay. We will come back to this, arrangement of B matrix also in a partitioned form. Before that, we will show a very interesting relationship between A and B matrix. What is it? Matrix A into B transpose will look like, see, we will have matrix A 1, 2, 3, 4, 7 elements here, and B transpose will have 7 elements here, okay, and this side will be loop 1, loop 2, and so on. This side will have the nodes. All right. Now, if you multiply elements of this and elements of this and then add them together, that will be AB matrix. Now, you see elements of this and elements of this will be summing up to 0. Can you tell me why? No, but why should that be 0?
Because plus minus will deal with plus minus.
Let us see. Let us see. Yes. These are the nodes. Now, a particular node, so particular node is, say this node, node 2 is connected with element number 5, element number 2, element number 4. Okay. Node 2 is having connection with 2, 4 and 5. Is that all right? So, these elements 2, 4, 5 in B matrix, how do they appear? 2, 4, 5. Now, out of these 3 elements there can be 4, 5 connections. All right. So far as the A matrix is concerned, in the row there can be, in this case there are 3 elements, non-zero elements, there can be 4, 5 non-zero elements, depends on the interconnection of that particular node. Is that all right? Now out of this only 2 elements will be involved in the B matrix. B matrix forms a loop. Is that all right? So from here, though there are 3 elements, you take this loop, then only 2 and 5 will be involved. 4 cannot be involved. 3 elements of a particular node cannot be involved in a single loop. I can have a loop going out like this and which will be involving 2. So either 2 and 4, or I can have a link with 4 and 5 or 5 and 2, but not all the 3. So only 2 elements of A in a row will be involved in elements of B. Now what will be the nature of those elements? For A, suppose they form all plus signs in the loop, means they are in the same direction in a particular loop. But then so far as the elements of A are concerned, one is going out, the other is coming in, then only it can form a loop. So A elements will have plus 1 and minus 1 signs, whereas in B it will be corresponding elements will be plus 1 and plus 1. So if you take the products, 1 into 1 plus minus 1 into 1. So it will be always 0. So A into B transpose is always 0. You take any row and corresponding columns, you take the products, it will be always 0. Need not be fundamental loop or any other this thing that A matrix after taking out the reference. It can be even with the entire A matrix, original A matrix, because for each row that relationship will be satisfied. So for each row and corresponding column of B, you take the products, it will be 0. So this is a very important relation. A into B transpose is 0. Okay. Now, what would be the procedure for developing a tree? I can choose n number of trees, alright. What is a possible algorithm for getting a tree? Otherwise, if you keep on connecting the elements into the network, you may not have a tree, because you may connect some elements on this side, some elements on the other side, they may not be connected. So I have to connect all the nodes, and there can be formation of loops also. I have to avoid loops. So we will discuss about formation of a tree, an algorithm for formation of a possible tree. For this, there are 3 elementary operations that we shall resort to, that is interchange of rows, multiplication of a row by minus 1, and then replacement of a row by sum or difference of other rows, by sum or difference of other rows. Sorry. Okay. This is precisely the procedure that you follow in the determination calculation of determinants of any matrix, is it not? Similar operations you use. So we shall be using these. Okay. These are known as elementary operations we shall be using for the formation of a tree. We will stop here for today. We will continue with this in the next class. Thank you.
Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shaped their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting. And the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls, with their blocks and wings connected by charming catwalks, remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous, and holistically inspiring. Where students, wherever they might be from, invariably come into their own, developing their individual talents, honing their skills to take on challenges with confidence, so they can move ahead in fulfilling their dreams. What makes IIT Kharagpur so unique is its environment. Undiluted by the diversions of metropolitan surroundings, the close-knit campus life enhances the entrepreneurial and innovative spirit of the achievers-to-be. In an environment that is so stimulating, it is only natural that down the years, IIT Kharagpur has consistently produced well-rounded individuals. Many of them are celebrities in their own right. Holistic grooming has had a lot to do with this. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute, whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, it is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire. Indeed, in this Golden Jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.